So in this discussion session, we will move our discussion towards linear order perturbation effects to higher order effects. As we recall in the previous discussions, we have learned about how to compute first order effects, and ultimately let me just write down the expression for you here so that we could just reflect upon what have we learned. At linear order of the perturbation parameter, at linear order of lambda, we have learned that the first order correction to the energy eigenstate, nth energy eigenvalue, is obtainable from taking the expectation of the perturbation Hamiltonian with respect to the unperturbed energy eigenstate, while the first order correction to the wave function of nth eigenfunction is obtainable from coefficient C n alphas, where alpha is not supposed to be the n set of numbers which will describe the state n over which we are trying to get the perturbation over, and effectively the psi alpha 0. So this is what we have learned, and these results are true at the linear order of lambda, that is the first order effects are these. Okay, now in today's discussion what we will try to do is to move in the domain of higher order effects, how to compute things at second order, let us say as an example, and from this philosophy we will see how to obtain things for higher order effects as well. So let us get going. So to start the story, we again rewrite the Schrodinger equation, which is the time independent Schrodinger equation, where the full Hamiltonian is H naught plus a perturbation lambda, the parameter lambda, times the Hamiltonian H1. This is the full change to the Hamiltonian, which is brought about by some parameter which we are calling lambda. As we have seen, it could be 8 upon mqc square for kinetic terms, and it could be v triple primed upon 3 factorial for harmonic oscillator about their minima if I try to go and try to see how the potential changes. So the lambda is the scale at which Hamiltonian gets perturbed with. We do not know what function of lambda the corrected eigenvalues and corrected eigenfunctions are, so therefore we write in terms of power series. Lambda order effect, lambda square order effect, because we do not know, the wave function remains the same or it changes, or if it changes then it changes with what function of lambda. It could be any function of lambda which satisfies the new differential equations. We do not know. Similarly, we do not know what energy eigenvalues do, how do they change. All we know is that they will change with the introduction of a new Hamiltonian term lambda, but what function of lambda is unknown to us. So therefore again the energy also we would expand in a power series about those parameter lambda. So ultimately we have this equation where the full Hamiltonian acts upon the full wave function and results in full eigenvalue multiplying the full wave function. And now we try to collect things order by order. At 0th order of lambda, the unperturbed equations came about. At the linear order of lambda, the previous two equations which we just saw got arrived. And now we want to know what happens at order lambda square. So again, from the left hand side and the right hand side, we will try to find out what are order lambda square effects. Okay, so I will try to collect things which are order lambda square. So order lambda square term in the left hand side can come from the following ways. If H naught goes and hits the order lambda square term over here, then I will get an order lambda square term. So that is one potential possibility, which is this H naught hitting the psi n2 over here. Fine. One more possibility is that this lambda times H1 goes and hits this. So then again I will get a lambda square with H1 acting on psi n1 term. So again we can see that on the left hand side these are the two possibilities. Either H0 acts on psi n2 or H1 acts on psi n1. So order lambda square term can be generated in the this way only from the left hand side. From the right hand side, again the same story. This number En0, which is free of lambda, can go and combine with the second order correction term to the wave function. So therefore, I can have En0 multiplying psi n2. One more possibility over here is that first order correction to eigenvalue goes and talks to the first order correction to the wave function itself. So En1 talks to psi n1, that is also order lambda square. And lastly, order lambda square correction in the energy eigenvalue. Unlike Hamiltonian, where I know what is the total correction, I do not know what happens to energy eigenvalues. They can be a higher function of lambda. So there is a lambda square possibility or higher powers of lambda possibility in energy eigenvalue. So therefore, lambda square En2 goes and hits the lambda independent term in the wave function, which is En2 multiplying the psi n0. So all these three terms are possible in the right hand side, which are at order lambda square, and only two terms are allowed in the left hand side, which are these two. Okay, so this is the story 4. This is the driving equation for the second order corrections. From here, we will try to find out two quantities, En2 and psi n2. Just like from first order story, we got to know about En1 and psi n1. All right. Now, how did we compute En1? We just took the projection of this equation with respect to psi n0. So that's what I will do again. I will take the bra psi n0 from left hand side and take the inner product of the whole equation. So if I take a bra psi n0 from the left hand side, this operator H0 acting on this psi n0 will give me energy eigenvalue En0, and then psi n0 will go and hit the psi n2. So that will be this term. Now the second term here, the H1 will get squeezed between psi n1 and psi n0. This psi n0 is not an eigenfunction of H1, so I will not get something like this. Here En0 came about because the unperturbed Hamiltonian was the psi n0, which was coming from the left, is an eigenfunction of H0. It is not an eigenfunction of H1, so I cannot do anything about it. I only have to keep it this way. Okay, so far so good. Let us see what happens in the right hand side. These are numbers in the right hand side. Here these were operators. So when I take psi n0, numbers will not do anything. They will just come out like before, and psi n0 will go and hit the psi n2. All right. Then across second term, again the same thing. The number will not do anything. It will just come out, and psi n0 will go and hit the psi n1. So I will get this term. And lastly, the third term En2 also is a number. It will not do anything. Psi n0 coming from the left will hit this psi n0. So here the psi n0 coming from the left and psi n0 already present in the right hand side here, they will just overlap and give me 1 because it is a normalized eigenfunction. So I will just get En2. So the first term is En0, psi n0 inner product with psi n2. The second term is En1, psi n0 inner product with psi n1. So two things, you again see the first term on the left and the first term on the right, they are the same thing, so they will get cancelled. The second term in the right hand side, which involves an inner product between first order correction of nth eigenfunction with the unperturbed nth eigenfunction, and that we have discussed that first order correction is orthogonal to the unperturbed eigendirection. So this is 0. They are orthogonal. The psi n1 and psi n0 are orthogonal. So all I am left with in the right hand side is just En2, and left hand side only one term survives, which is H1. This time it gets squeezed between psi n1 from the right and psi n0 from the left. Remember, En1 was what? En1 was H1 squeezed between psi n0, psi n0. This time there is a subtle difference. It is not squeezed between psi n0 and psi n0, or it is not squeezed between psi n1 and psi n1. On one side it is psi n0, unperturbed one. On the right hand side there is a perturbed one, psi n1. the correction. That gives me the second order effect. And from first order perturbation theory, I know everything about psi n1. That means psi n1 has to be written in the basis of unperturbed eigenstates like this. Okay, so just a second. So this is psi l n0 in the product. So, or better to write, this is psi, this CNLs are the off diagonal elements of the perturbation Hamiltonian squeezed between n and l from left and right, and the energy difference in the denominator. So I know everything about psi n1 from first order perturbation theory. So I feed that information of psi n1 into the expression of En2. So this whole thing over here is nothing but psi n1, which we had derived in the previous class. So now you see there is a h1 which is operator, there is this h1nl which is a number. This is a operator squeezed between two states. Remember, h1nl meant psi n0 psi l0 h1 psi n0. So this is already a complex number. So this number will not do anything, it will just remain like that. So ultimately this h1 operator will get squeezed between psi n0 and psi l0. So I will get, so there was h1nl already present in the expression, and from this operator, left hand side vector and right hand side vector, I will get another term which is psi n0 h1 psi n l0, which is nothing but h1 ln. So you see this is h1 ln, and already there is a h1 nl, the off diagonal terms of row and columns reversed. And since Hamiltonian is a Hermitian operator, their off diagonal elements are complex conjugate of each other. So h1nl and this combined gives you h1ln. They are just complex conjugate of each other. Therefore, you will get a mod square of one of them, h1ln mod square. So therefore, we can again see, if I just clean up here, we can again see that feeding the information of the first order expression gives me the second order correction in the energy eigenvalue. En2 is obtainable from psi n1, and that psi n1 information gives me what is the second order energy correction. Okay, all right. Similar game you can play in order to know what is psi n2. Psi n2 should be some superposition of L not equal to n, Cn, let us say 2 means second order effect, and psi L0. The same game what we played for the first order theory. In this case also, how to obtain Cn2L will be in the same spirit what we computed, from where we computed the first order correction. In the same way you have to do that. So from here we can find out, I'm not going to show the expression because for our discussions of future sessions, this information is not really required. So this you can take as a homework exercise for you, that how to obtain Cn2L, and similarly how to obtain the third order correction, third order energy eigenvalue shift, and those kind of things. You will see a recurring feature. What is the recurring feature? The recurring feature, it will be this, that first you obtain the first order correction to the wave function psi n1. From there you get the second order correction to the energy eigenvalue. Now if you get the second order correction to the wave function psi n2, that will tell you about the third order correction to the energy eigenvalue, and so on. So it builds up. So ultimately one wave function's correction tells you higher order energy eigenvalue shift, and so on. But in this way they get related in some way, that En2 depends on certain feature of psi n1. This en0 minus el0 has appeared in the second order correction because the same quantity appeared in the denominator of the first order correction to the wave function. And you can see if you try to build upon higher order corrections, it will keep appearing at here and there. So in CNLs, this denominator came. In En2, the denominator comes. In En3, En4, psi n2, all these things, this factor will come in the denominator. So setting up this is just algebraic steps. Starting from this equation, you can now collect order 3, lambda cube order term, lambda 4 order term, and keep using the previous information, and you will set up for the higher order correction. So this is the mechanism or the machinery with which you can proceed along the higher order effects, which is technical but nothing more conceptual than that, but for the feature which you should pay attention to. For that, I should again write down what is psi n1. Once again, I'm just rewriting this equation cleanly here. Psi n1 is nothing but summation over L, where L is a marker for all states which are different from n. And then H1NL, which I had missed over here, H1NL it should be, divided by En0 minus EL0, and then psi L0. So this is my first order correction to the wave function, and while this expression is the second order correction to the energy eigenvalue. Both of these come with denominator En0 minus El0, where L is being summed over on all other states which are there in the system. Not necessarily only first few states. All the states have to be summed over. Now, L cannot be n. That I should not include the wave function for which I am trying to get the correction. But in certain systems, it can so happen that there is a different eigenfunction which has the same eigenvalue. So accidentally, despite psi L0 not being equal to psi N0, still it is possible that you will have En0 equal to El0. We have seen examples like that. For example, in hydrogen atom, we know the ground state is 100 and it has a single state. But first excited state n is equal to 2. Actually, there are 4 states there. 200, 210, 211 and 21 minus 1. So they have same n values, but they have different L values and M values. It so happens that energy eigenvalue computation does not depend on L or M. Energy eigenvalue for hydrogen atom is only a function of M minus 13.6 eV upon n square. So it is only a function of n. It does not care about L or M. So therefore these states are different from each other, but they have same n. So therefore they will have same energy. So therefore in hydrogen atom, a system like hydrogen atom, you can see that such a possibility arises that despite I am talking about different state, I will end up getting a term in the denominator which is 0, and therefore this will blow up. First order correction will blow up if En0 is El0. If the first order correction blows up, second order energy eigenvalue also blows up. Third order energy eigenvalue also blows up. Second order wave function correction also blows up. Because as we discussed, there was a recurring theme. One thing sets the other. So if that happens, no longer I can say these corrections are small. If things start blowing up, psi n1 blows up, En2 blows up, I can no longer trust this perturbation expansion. So therefore, the robustness of the perturbation theory is under question. So the perturbation theory will break down if such a thing happens. So I cannot use this perturbation theory machinery which we have developed if it so happens that I am talking about a system where two states have the same energy despite being different states altogether, like hydrogen atom. And this gives rise to a aspect or the approach of a degenerate perturbation theory. The approach what we discussed will work fine for all the systems where one state has a unique eigenenergy. There are not two different states with the same energy. If that happens, your system is safe. You can do the perturbation theory. But if you have system where degenerate eigenstates are there, then you have to be careful. You cannot use these formulae, because these formulae are not made to come to terms with different states of same energy. So therefore, we go to the domain of a degenerate perturbation theory. Okay, so degenerate perturbation theory will be a theory again in which, let us say, two states or more states in principle have the same energy. Okay, and the problem was the theory will become perturbatively problematic because these terms which are supposed to be small start becoming very large. So I do not have a technique to keep them small in order to make the sense of perturbation theory. Otherwise, I have to give up on perturbation theory. So one way people thought about that, fine, the denominators are going to 0 and these things will blow up, but it will blow up only when the numerators are finite. Then only some finite upon 0 will blow up. But suppose the numerator also goes to 0. In that case, then I have no issue, because if that goes to 0, I will come back to the story where we started from here. Psi NLs, which we wrote down somewhere, H1 NL here. If that goes to 0, then it is 0 by 0, which is not necessarily infinity. It can be small number or finite, and therefore things could be under control. Okay, and if I go back to the genesis of how did we compute the En2 and whatnot, so En2 was made up from psi N1, and psi N1 involved this H1 NL. If H1 NL is 0, then psi N1 will also become 0, at least for those subsector. So the idea is that we will not panic just on seeing the degenerate states. We will first check and see if H1 NL is 0 or not for those states which are degenerate. So I will take N, state N and state L, which have the same energy corresponding to H0. But I will try to write down the perturbation Hamiltonian in this subsector across N and L subsector. So in this two-dimensional subspace, the perturbation Hamiltonian's diagonal terms will be H1NN, H1LL, and off diagonal terms will be H1NL and H1LN. Now, if it so happens that these terms are non-zero, they are finite, then I know we are in a problem, that perturbation theory will be problematic. However, a remedy to this is already available. The statement is, suppose these terms are non-zero, can I do something to make them to go to 0? The answer turns out to be yes, we can do that. Actually, what we can do, we can change L, the state L, to something called L primed, which is a linear combination of the two degenerate states, N and L. Some coefficient times alpha times N plus some coefficient beta times L. The new L primed, you can verify it has the same energy like En0, El0, call it El0, with L primed as well. So not only N and L have the same energy, even L prime also has the same energy as far as the unperturbed Hamiltonian is concerned. You can verify that if this is eigenstate of Hamiltonian with energy En0, and this is also eigenstate of Hamiltonian with energy En0, then this combination is also an eigenstate of the Hamiltonian with the same energy. So when I go from L to L primed, I have not done any energetic changes as far as H0 is concerned. H0 does not see its different states. However, while doing so, I can carefully select some alpha and beta such that H1L primed n, the off diagonal term in the new wave function basis, is 0. That means I want this to be 0. H1L primed n is 0. So I compute what is H1L primed n. That will be H1 squeezed between L primed and n. That means this is the L primed and this is the n from the left, and I want this to be 0, which I can open up. This term is nothing but H1NN, and the second term is nothing but H1LN, because L comes from the left, H1 is in the middle, N is from the right. The other way, L is on the right, H1 is then in the middle, N comes from the left. So I get a H1LN. This I want to be 0. If this is 0, then the coefficient alpha and beta should be related like this. The value which was there, which was not 0, I will just take the ratio of this and the ratio of the eigenfunction, the ratio of the diagonal element to off diagonal element. That will tell me what should be the ratio of alpha and beta, and therefore that will make the Hamiltonian, perturbation Hamiltonian, not H0, the perturbation Hamiltonian diagonal in this new basis. So therefore in this new basis, H1L primed n or H1 n prime n times L prime, these off diagonal matrix elements will be 0. Therefore this term will go to 0, and the risk of the denominator going to 0 will not hit us anymore. So the idea is, you should, whenever you have a degenerate states, you should check the Hamiltonian of perturbation first and see if the off diagonal terms are 0 or not. If they are 0 to begin with, you don't have to worry about, because despite the energy eigenvalues being the same, the 0 in the numerator saves you. If they happen to be non-zero, then you should try to find a new basis in the degenerate subspace. Degenerate subspace meaning all those states which have the same energy corresponding to H0. You write down the perturbation Hamiltonian in that basis and try to see if this is diagonal or not. If they are not diagonal, do something about it. Try to diagonalize it. While you try to diagonalize it, you are just linearly superposing n and L. This does not change anything corresponding to unperturbed Hamiltonian. So the idea is, we will always write down the perturbation Hamiltonian in a diagonal degenerate basis. Okay, let us see one example and to get the point. For example, in the last discussion session, we computed the first order correction, let us say En1, for n is equal to 1 of hydrogen atom. That is what we computed. Suppose I want to know what is En is equal to 2, the first order correction to that exercise you can do. But here again, you can compute things from the formula which we had learned, n is equal to 2, and then you have to tell which LMs you are talking about. N is equal to 2 and which LMs you are talking about. This will be the first order correction. But if I want to know second order correction to n is equal to 2, second order correction, or if I want to know what is the first order correction to the wave function. So these things are problematic here, because n is equal to 2 comes up with an energy E n is equal to 2, which are shared by 4 states: 210, 21 minus 1, 211 and 200. So all these have the same energy. So therefore we are talking about degenerate perturbation theory here. So how to find out whether the perturbation theory is stable or not, or if we can do something about it. So again, look back at the same problem which we computed in the previous class. I will just go back to that. We were considering a hydrogen atom put in external electric field. The Hamiltonian was E times phi, or compactly written as E times Z with a minus sign. That was my perturbation Hamiltonian. For this Hamiltonian, I want to know what is the first order correction to the wave function for n is equal to 2, and what is the second order energy eigenvalue shift for n is equal to 2. So I already know that the perturbation Hamiltonian, the state which I am talking about, suppose I want to know for state 200, what is the shift in the eigenvalue at the second order and what is the first order shift in the wave function itself. In both the cases, there is a problem because for 200, there are other states which are different from it. For example, 210, 21 minus 1 and 211, which have the same energy as 200. So what I should do, I should first try to check whether H1 is diagonal in this degenerate subspace or not. So I compute the matrix H1 in this degenerate subspace. 200, 210, 211, 21 minus 1, and the columns, row and columns are like that. If you do this exercise, which I am just skipping, but you know how to compute, you will take H1, what is 200, 200, it will go and sit here. You will find out that this number vanishes. Actually, all diagonals vanish. And not only all diagonals, most of the off diagonals also vanish if you do this computation. Only thing survives is H1 squeezed between 210 and 200. That survives with a value minus 3e a naught and its off diagonal counterpart E squeezed between 200 and 210. Okay, so these are just off diagonal elements. So ultimately, apart from this sub block, the perturbation Hamiltonian is already diagonal matrix, but for this small two-dimensional 2 cross 2 dimensional subblock. So what we want, we can just focus on this dimensional subspace where the perturbation Hamiltonian looks like this, and want to know if we can diagonalize this. 200 and 210 basis does not diagonalize it. So can I find a new basis psi A and psi B, let us say. Here I will get a psi B and psi A from a linear superposition of these two wave functions. Can I combine them in such a way to land up on two different states psi A and psi B such that they become diagonal? Okay, the idea is clear. You have to just combine these. While you are combining, the new state will have the same energy as each one of them because they are degenerate eigenstates. Their superposition does not change their unperturbed energy eigenvalues. So you combine them and try to find out if it is possible by linear superposition of 200 and 210 to diagonalize this. And you will learn that indeed you can do that and you can diagonalize this Hamiltonian. Actually, this 2 cross 2 dimensional Hamiltonian can be diagonalized in a new basis called psi 2a and psi 2b. The other two-dimensional subbasis was not needed to be changed because Hamiltonian was already diagonal in this subspace. Only where it was not diagonal is across this and across that. So therefore, I have changed those two states to psi 2a and psi 2b. This is also psi 2a, this is also psi 2b. Other things remain as they were. So indeed it is possible to diagonalize this perturbation Hamiltonian for n is equal to 2 subspace, and it so happens that psi 2a is just addition superposition of the two state 200 plus 210 by 1 by root 2, and psi 2b is the difference between 200 and minus 210 with 1 by root 2. If I declare psi 2b and psi 2a as my basis so effectively the four states of the hydrogen and which were 200, 210, 211, 21 minus 1 are being replaced into psi a, psi 2a, psi 2b, 211 and 21 minus 1. All these have the same energy to each other and all these have also same energy to each other, but this basis has a benefit that the perturbation Hamiltonian is also diagonal in this space. So therefore, you can do this business carefully over there. There is no problem. The diagonal elements of the perturbation Hamiltonian therefore tells you about the first order correction. Now the perturbation theory is safe. So you know, due to perturbation, the Hamiltonian of the energy eigenvalue for n is equal to 2 will change. Previously, we had learned that for n is equal to 1, it did not change. But for n is equal to 2, it will change. It will change for 2 of them, it will change. For 2 of them, it will not change. Out of these 4, the 2 of them it will change and 2 of them it will not change. For 1 of them, it will go up by amount 3e_a0, and for 1 of them, it will go down from by minus 3e_a0. So if I draw it pictorially, let me say over here, if I draw it pictorially, previously there were 4 states, one over each other. All of them were having the same energy. Now it so happens after the correct application of the perturbation theory, degenerate perturbation theory rather, where I go to a correct basis. First I go to a correct basis again, which have all the same 4 states as the same energy. So this basis was for 2, 0, 0, 2, 1, 0, 2, 1, 1 and 2, 1, minus 1, while this is for psi 2a, psi 2b, 2, 1, 1 and 2, 1, minus 1. All these have the same energy. There are 4 states here and there are 4 states here as well. All of them have the same energy as far as H0 is concerned. But once you apply H1, perturbation theory on this basis is ill-defined. Perturbation theory on this basis is well-defined. And here it so happens that 2 of the states do not change at all, so their energy remains the same. One state goes up by energy by this much amount, and one state goes down by energy minus 3e_a0. So ultimately the 4 states here, 2 of them go here, 1 of them goes up and 1 of them goes down. And this is a result which we knew from correct usage of perturbation theory on correct basis. All right, I could not have applied perturbation theory on this because things were blowing up on this basis. So it is a good idea to go to a correct basis and then find out what happens to those terms. Okay. One more example, which is very famous example, something called the spin orbit coupling, where a new term due to the spin of the particle and its angular momentum around the nucleus, they talk to each other and they give rise to a term like this. You can look at the textbook by Griffiths, Introduction to Quantum Mechanics, chapter 6, to see the conceptual reasoning for this term. So in this course, we are not talking about quantum mechanics from the perturbation theory approach completely. We are just reviewing it. So therefore, I will guide you to look for where does this structure come from. But ultimately, it comes like this. And we know that L dot S can be written as J square minus L square minus S square divided by 2. And this comes from the decomposition of the total angular momentum as orbital angular momentum plus spin angular momentum. So therefore, you know that this is operator J square, this is operator L square, this is operator of S square. So if I take a state which is an eigenstate of J, L and S, that will be an eigenstate of full H1. So therefore, I can choose if I can choose the state in a basis where I have J, L and S, then I know the Hamiltonian, this will be the eigenstate of the Hamiltonian. Eigenstate of the Hamiltonian meaning perturbation Hamiltonian. This will be eigenstate of the perturbation Hamiltonian as well. And if it has an information of n, then it is eigenstate of unperturbed Hamiltonian as well. So if I write things in a basis n, j, l, s and z component of the total angular momentum mj, then I know this is a basis in which H0 is diagonal as well as H1 is diagonal. So H1 happens to be diagonal in this basis. Despite this being a degenerate theory, that means n is equal to 1 even, I can have a J which is L and S. L for n is equal to 1, you know, n is equal to 1, L can only take value 0. So L happens to be 0 for n is equal to 1, but S has a value 1 by 2, spin half, electron is spin half object. So even for n is equal to 1, J can take a value half. Since S is half, J is L plus S. So therefore the magnitude of J is magnitude of S, which is half. In the sense of eigenvalue, it is half into half plus 1, but magnitude of J vector is magnitude of S vector. And its Z component is twofold. It could be plus half or minus half. So there are two states even for n is equal to 1. Actually, that is how this 1s1 and 1s2 come about in S is equal to n is equal to 1 thing. One is electron up and one electron with spin down. They will both have the same energy. So first state, ground state, two electrons can live. This is a degenerate perturbation theory, right? Because 1s1 state and 1s2 state both have the same energy. Yet, it so happens this particular Hamiltonian is already diagonal in this basis. So I don't have to worry about validity of perturbation theory, and I can compute my things like first order correction to the wave function, which you can go ahead and compute things which are fairly straightforward. You might have done it at the quantum mechanical level as well. It is a good idea to revise. So I will just take the perturbation Hamiltonian, squeeze it between the energy eigen states. I do not have to worry anymore because perturbation Hamiltonian is already diagonal. So I do not have to worry whether the perturbation theory is valid or not. Then you will see that this J square, this L square, this S square acting on this eigen state gives me J into J plus 1, L into L plus 1 and S into S plus 1. And then 1 over R cube which comes about gets squeezed between this N and L. Effectively, this operator acting J square, L square, S square gives me this factor J1, J into J plus 1, L into L plus 1, S into S plus 1 times H square by 2, and the state back N, J, L, S and J. Now these are numbers, so it will go left, and 1 over R cube will get squeezed between these two states. But it so happens that 1 over R cube operator does not care about your J value, does not care about your spin value, does not care about your Nj value. Only things it care about is N and L. So this N, L, N, J, L, S, M, J could be written as NL times J, S, M, J as a direct product. And when I squeezed 1 over R cube across this state, the J, S, M, J part does not undergo any operation. They will just plainly get inner product with respect to each other and give me 1, and 1 over R cube will come in between this. And this is a good exercise. If you have forgotten about quantum mechanics computation in hydrogen atom, you can go back and do this. You will get this as an answer. So I'm not telling you how to get it, because in this course we are just talking about the essential feature. Perturbation Hamiltonian happens to be diagonal in this basis if I choose. Otherwise, if I started from some different basis, the idea would be to do a basis transformation and land up here in this correct basis, N, J, L, S, M, J basis, which is degenerate but diagonal. So therefore, we are safe. So therefore, I know in order to deal with any system, I will go to first check whether my system is degenerate corresponding to unperturbed Hamiltonian H0. If it is, I will always try to construct a basis in the degenerate subspace where the perturbation Hamiltonian becomes diagonal. Remember, a crucial point is to remember, we are not demanding that H1 becomes completely diagonal. We are not saying that it should be diagonal completely. If it is good and well, but if it is not, I'm not saying that we should diagonalize it completely. I'm saying we should diagonalize it in the degenerate subspace only. For example, suppose two states have the same energy, this and this. The Hamiltonian here should look diagonal. here and here, it could be off diagonal terms, can be non-zero. So I'm not demanding H1 to be completely diagonal. We are just demanding that it should be diagonal in the degenerate subspace. So that is the idea of perturbation theory, that if I want to know my system completely through perturbation theory, I should check whether we are talking about a degenerate system or a non-degenerate system. Non-degenerate system, life is easy. We can compute things as we learned. Degenerate systems, I should make sure that the perturbation Hamiltonian becomes diagonal in the subspace, in the limited regime of the full matrix description. In this subsector, it is diagonal. If it is diagonal, then I can relax and my perturbation theory is safe. We can do computations like before. Okay, so this is a review. We are stopping here for the time independent perturbation theory. We learned about how to develop perturbation expansions in energy eigenvalues and energy eigenfunctions. We learned how to take out terms on left and right side compared to various powers of lambda. Then we learned about how to take projections of those equations along psi n0 or psi l0, and from there we got corrections to eigenvalues at different orders and correction to wave functions at different orders. Okay, we have seen a couple of examples as well for hydrogen atom and harmonic oscillator. Okay, fine. So we stop over here and this ends the review. It is a rather quick review of a time independent perturbation theory. In the next class onwards, what we will do, we will learn about time dependent perturbation theory approach, because that is more relevant for matter field interaction, which we will discuss about in coming lectures. Okay, so we stop over here for today.